we'll see the definition of annihilator of a subspace W of a vector space V. So if W is the subspace of V, then the annihilator of W, denoted as A of W, is all those linear functionals which annihilates all the elements of W. That is, f of W is equal to 0 for all W in capital W. Now what we can say about this A of W? It's a subspace of V cap, and whenever U is contained in W, U is a subspace of V which is contained in this subspace W, then the relation between the annihilators, their annihilators, is A annihilator of W is contained in annihilator of U. So if W is a subspace of V, then A of W is given by this. Now first we want to show that this is a subspace. So we'll have to describe what A of W, so that is what is done here. And we have to show that it is non-empty, and then we have to go for checking the criterion. So because 0 functional, it's a linear collection of all linear functional, so 0 is an obvious member of A of W, because 0 will take any vector to this 0 for all W in W. So A of W is non-empty. So that is the job of 0 function. It will take any vector to, in this case, V cap means V to F. So that means it's a scalar. This 0 is regarded as a scalar. Remember that it can also be regarded as a vector when you view F as a vector space. So you have annihilator of W is non-empty, and the criterion to be checked is for F comma G belonging to A of W, you have to have alpha F plus beta G belonging to A of W. So this has to be established. Now any element can belong to A of W provided alpha F plus beta G of W is 0. So that is what is verified here. This is point-wise addition that is used here, and the scalar multiplication in V cap that's used, and F of W 0, G of W 0, so that's used, and you have alpha F plus beta G of W is to be 0, and therefore this is a member of A of W, and therefore A of W is a subspace of V cap. Now coming to the second one, we want to show that A of W is contained in A of U. So you consider F in A of W, which means that F of W is 0, and this is true for every W in W, but inside W only where U is present. So even for all the elements of U, this relation holds. So F of U is equal to 0. This implies that F belongs to A of U. So A of W is contained in A of U. Now this is the last theorem of the section. If V is finite dimensional, W is a subspace of V, then W cap is isomorphic to V cap over A of W. Actually speaking, we will be showing that V cap over A of W is isomorphic to W cap. And we have to show even that dimension of A of W is dimension of V minus dimension of W. Right, two parts are to be established. First we will establish this by considering, we will consider mapping between V cap and W cap. We shall define a mapping between these two and show that this mapping is onto homomorphism. It should be onto homomorphism with kernel A of W. If the kernel is A of W, with kernel A of W, then V cap over A of W will be isomorphic to, it will be isomorphic to W cap. So this is the idea. So between V cap and W cap, once we define a mapping, we have to show that that's onto homomorphism with kernel A of W. So you define, how are we going to define? So for this we are using restriction mapping. The restriction mapping is this, it is defined this way. You have, see, we consider F to be a mapping from V to F, capital F. We consider small f, suppose I consider small f to be a linear functional, which means it's a mapping from V to F. Now in V we have W to be a subspace. In V we have W to be a subspace. So we know very well that how my F takes all the elements of V to F. So what do I mean by restriction? I'm restricting F to W. So from W to F we are going to define. So that mapping is restriction mapping. How it is defined? For convenience sake, this is denoted as F tilde. And what is the job of this F tilde? How it is defined? It will take any element W in capital W the same way as the same W is taken by F. How this F takes all the elements in V? Known. In particular, how it takes the elements of W? Known. So with the help of that, you define your restriction mapping F tilde of W. So F tilde of W and F of W are the same. So that is how restriction mapping is defined. So in this way we define our T. So we name this mapping, the rule, how it is defined, that as equation 1, and F tilde of W is equal to F of W for all W in W. So that is named as equation 2. Now this rule being defined by us, we have to show that it's well defined. So for which we consider two functions to be, linear functionals to be equal. F is equal to G, which means mappings are equal means the corresponding images should be equal. So in particular, this is true for every V in V. So in particular for W and W also it is true, which means that F tilde of W is equal to G tilde of W. And so that in turn implies F tilde is equal to G tilde, because this is true for every W. As images are equal, mappings are equal. But this stands for FT and this stands for GT. So T is well defined. For homomorphism, Dragata addition and scalar multiplication, these are the conditions to be checked. So we consider the LHS of this, which is by the definition, by equation 1 is nothing but F plus G tilde of W. And so this is nothing but F plus G of W. For convenience, again convenience sake, suppose we take this as say some P tilde, that is F plus G is P, so that P tilde you will have. So that the definition will go like this: P tilde will be equal to P of W. That P stands for F plus G. So that is how you get this. And pointwise addition and W cap gives me this. And this by equation 2. By equation 2, it is F tilde of W plus G tilde of W. And by the definition of addition again in W cap, we have this to be F tilde plus G tilde, pointwise addition. So we have this. As the images are equal, the mappings must be equal. So you have F plus G, the whole tilde to be equal to F tilde plus G tilde, and that in turn gives what is required. That is the first subdivision. And for the second one, we shall consider alpha F tilde of W, which is alpha F of W by 2. And by the definition of scalar multiplication in W cap, you have this. And by equation 2, F of W is same as F tilde of W. And so you have this. So you have alpha F tilde to be equal to alpha F tilde. And that in turn gives this. This proves the second part. Now, T is a, because of these two conditions, your T is a homomorphism. Well, now, being a homomorphism, we can talk about the kernel. Kernel T is all those F and V caps such that Ft is the 0 scalar 0, because it's 0 functional. V cap to W cap it's defined. Okay, so you have this again to be 0 functional. So F tilde is equal to 0 functional, and so mappings are equal, so images are equal. So this is what we get, and this is nothing but your FW. Now we cannot easily have our T to be onto, for which we have the following discussion. So you have in W cap, you consider some H. For this you have to find in V cap a pre-image. For this H, you have to find one pre-image in F, so that you will be able to have Ft to be equal to H. That is F tilde. That is F tilde is equal to H. So this is what we need to establish in order to have T to be onto. Right. So you consider H in W cap. Then this is what you have to show by lemma 4.2.21. Since W is a subspace of V, which is finite dimensional. W is a subspace of V. Even though it is not mentioned, it is understood. W is a subspace of V. Dimension of W is finite. Dimension of W is finite. So we shall take it as, say, some M. So we can have W1 etc. Wm to be a basis of W. So then it can be extended to a basis of V of the form W1, W2 and so on, V1 etc. Vr, where R plus M is equal to dimension of V. Now let W1 be subspace of V spanned by, we are introducing another subspace. Already W is there. Now that we introduce another subspace W1 spanned by V1 etc. Vr. Now we have already proved in section 4.2 in the solved problem 5 that V is the direct sum of W and W1. So if H belongs to W cap, you are going to define, so this is introduced by S. So we are going to define our F in V cap in this way. F of V is equal to H of W. Now the question is, can we define like this? The answer is affirmative. The reason is, once you have V in capital V, because capital V is the direct sum of this and this, you can always have V to be an element from W plus and an element from W1 as W plus small w plus small w1. So in that way my V is connected with W. So this connection, is it defined? Yes, that's because of this. Okay, because V should involve W. Yes, it involves. So there is a point in describing your F in this way. And F is in V cap means this is a scalar. H already belongs to W cap, so this is also a scalar. So there is a sense in defining your F in this way. Now it is easy to see that F is also linear functional because H is linear functional. So this is rewritten as F tilde. So H is equal to Ft, and so T maps V cap onto W cap. Now this is onto homomorphism with kernel Fw, and therefore by the fundamental theorem on homomorphism or first isomorphism theorem, V cap by Fw should be isomorphic to W cap. Now since this is isomorphic to this, we have to have both of them to be of the same dimension. So dimension of V cap minus dimension of Fw is equal to dimension of W cap, that is by theorem 4.2.23. And dimension of V cap is same as dimension of V, so we have this. So rewriting this, that is taking this to the other side, we notice that dimension of Fw is dimension of V minus dimension of W. How this could be interpreted? This W is a subspace of V, so you write that. So Fw, dimension of Fw is dimension of V. It's a subspace of what? That should be written here, and the same thing is to be written here. So you have dimension of Fw is equal to dimension of V minus dimension of W. So in case that we want to have, say, dimension of A of W, say, on the same line if we proceed, let us see what we get. Dimension of A of Fw. We know very well that this is a subspace of V cap. So as per this argument, we should have here dimension of V cap, dimension of V cap minus dimension of A of W minus dimension of A of W. So you have to have, this is dimension V cap, but you have to have dimension of V cap to be same as dimension of V, and from the previous discussion we have dimension of A of W to be dimension of V minus dimension of W. So we have within bracket you have, so this and this will get cancelled, giving minus of minus plus dimension of W. So dimension of A of W, A of W will be equal to dimension of W. So this is a consequence of this discussion. So now we will establish this. Remember, your W is finite dimensional, and annihilator of V cap is finite dimensional, V double cap is finite dimensional. This is a subcollection over there, in fact a subspace, and therefore this must be finite dimensional. So whenever we have two vector spaces, whenever we want to have two vector spaces to be equal, if they happen to be finite dimensional, it is enough we check these two conditions. The conditions are one is contained in the other. So in this case we are going to show that W is contained in A of W, and both of them are of the same dimension. So this is by the solved problem 4 in section 4.2 this argument comes. Okay, so now to establish this, you consider W and W, which means that f of W is equal to 0 for all f in A of W by the definition of A of W. Now this in turn implies W belongs to A of W. So how this happens? Now you go back to this. Now A of W you have described in this way. So in the same way A of W can be described. So already we know that TV it is the collection of all linear functionals T suffix V belonging to V double cap such that TV of f is equal to 0 for all f in A of W. Okay, and then now this is same as f of V is equal to 0 for all f in A of W. But we have already established that there is a relation between V and V double cap, namely V is isomorphic to V double cap. So you can regard the elements which are actually like this as this element V, and all these remain the same, right? So now to prove this part, you consider W and capital W. So automatically for any f in A of W, by the definition of A of W, f of W has to be 0, right? Because I have considered my f in A of W. So by the definition of A of W, f of W should be 0. So whenever I have f of W to be 0 for all, f of something to be 0 for all f in A of W means this something should be present in A of W. So your W belongs to A of W. So W is contained in A of W, and both of them are of the same dimension because of this. So by the solved problem in section 4.2, we conclude that annihilator of W is W.